let them do the talking and put you in the audience instead. So it's going to be a mix of different views, different application market segments. We're going to have a presentation on system Verilog as well, using VUnit with system Verilog. I've already seen quite a few VUnit users here today. There tend to be a lot of discussions offline as well, so if you're interested in engaging in those kind of discussions, I suggest that you gather around the submittable apps. I will be there and hopefully a bunch of other people. So first out today is Sebastian Hellgren from CodeCache. He's going to talk about introducing VUnit to large organizations where there are already a lot of developers doing something else. They already have a lot of code, existing code. I think you're also going to speak a bit about verification components. Great.
So, my name is Sebastian Hellgren. I'm the owner and operator of CodeCache Linköping AB. And today I'm going to speak a little bit about VUnit integration and verification components. So first up, it's a little bit about me. I have so far 13 years of FPGA experience in various contexts. And currently I have the opportunity to work with Hitachi Energy's power control and monitoring systems. CodeCache, we are a small consultancy company focused on FPGA development. We're located in Linköping. As a side notice, we have a very interesting thesis project, which I can discuss offline with you guys if you're interested. So today's agenda, we will first talk a little bit about code organization, because first off, when you enter a new organization, the organization of the code itself might not be optimal for introducing VUnit and introducing common simulation and build scripts and so on. Then I'm going to talk a little bit about VUnit integration, and lastly, a concept which many of you already are familiar with, which is called verification components, and how those are built using VUnit's library. So, for the current context here, we have Hitachi Energy's HVDC control systems. These are very, very large systems. They basically transform AC to DC and vice versa. And it's a very intensive testing process. So it's absolutely essential to catch errors as early as possible, and especially interfaces, since when you have systems of this scale, there are naturally a lot of interfaces. So, reorganizing code and moving stuff around might not be the most exciting part of an assignment or a job, but if you take the time to come up with a modular and extensive approach, it will save lots and lots of time later down the line. This won't be new to many of you, but it's nevertheless worth discussing. So what we did was basically move to a single repository, or at least into a structure where we can easily access and share everything from a single directory structure. It's not possible in all contexts and all projects, but for us it was possible, so we saw the opportunity and took it. So by having a single repository, we merge all the available code and modules and scripts and so on, and throw out stuff, we introduce stuff, we glue stuff together, and basically ensures that every code we have written can coexist in a nice manner. So effectively we reduce code duplication and reduce the total maintenance cost of the code by having less duplicates of code and merging utility libraries, test bench utilities, Python scripts, whatever. By doing this, it's also much easier to have one single controlled build and simulation environment instead of multiple scripts. Like if you have silos for each project and each project have their own build script, we move to a single script, which is easier to maintain, and we can easily extend, and we can reduce the maintenance burden on the developers themselves to build the build scripts. And instead they can focus on writing the code, and we have a common effort to introduce new features and code into the build system itself. So then we also have one version of the build system, which means it's full traceability. We have our build system that we can see what kind of build system, what version of the build system that each and every release was written with by tracing the hash ID of the released code. So we can check out and see, there was an error in the build script, for example. So it's not just for the code, it's also for the build and simulation environment. By having a code in one place, we can also we have one simulation script. So when a developer makes a change in one module or one file, we can run all test benches and see if he has introduced errors in unintended places. Also, it makes it much easier to do code review on the code as a whole instead of isolated silos and have multiple reviews and multiple places sharing diff files and etc. We have one repository, we have one tool, we have one web view. You can see all the impacted changes. You can trace them, so it makes much easier. One byproduct of having a single repository is it actually forces us to collaborate more. It forces us to talk to each other about what code and modules and how it works. And then you might open up communication channels between different projects that share the same modules and they want to have. And basically they may conclude that we can use the same version of the module if we do this and this approach. So we are forced to collaborate. Okay. So then we started by organizing the code. So we organized it into modules and projects. Each module has its own configuration scripts, VHDL files, IP cores, ticket files, etc. And unfortunately, each module may also have different version branches, which is quite common for legacy code. This may introduce dependency issues. If you have, for example, nested build scripts, which one script acts as another module's build script, and in turn, and you may end up with different revisions of one module in one project. So this is an issue. So then you have to instead of versioning the module, you have to version the module's dependencies also. So we axe that, and instead we define one set of module versions per project in one file, which is central for the project, which pinpoints the version of each module. So one project may only have one version of one module per project. And then we have this single source of information for the module versions. This, of course, by having some projects may depend on the same version of a module, but so those projects, so we may double simulate stuff. But we have decided to roll with this and be fine with it and build upon it and optimize and reduce the module versions later. Instead of having the Big Bang approach, everything must be perfect from the start. No, that's not how we work. So we do this as a stepping stone towards moving towards one version, one module version. So we can have one main line of each module. Okay, and now that we have organized our code, it's fine and dandy. We move to integrating VUnit. And as Wally says here, it's also important to test your test and build scripts. Python tests, anyone? And why did we decide on VUnit? Basically, it was a combination of different factors. It's Python-based. Python is nice, and most developers prefer to work with that over bat scripts, I suppose. It finds test message automatically, so it's easy to add new tests for developers. It's easy to configure test cases with many supported simulators. It's also quite flexible and very non-invasive in your design, which doesn't enforce strict test bench structure on your code. You can generate many useful reports, and it also has many convenient HDL utilities such as arrays, queues, BFMs, verification components, logging utilities, etc. So to organize our code, we used an open source framework called TSFPGA. It's basically Python, written in Python, and it handles all the HDL, constraints, IP cores, symlib compilation, etc. It has a nice Python interface for the bottom, and it also integrates very well with VUnit. So the modules are organized connected, and we access them via TSFPGA. So our test benches and test configurations are forwarded to VUnit using the standard VUnit command line interface. And then using the same framework, accessing the same modules, we can also access our build scripts. So we have a single source of information for all our modules here. So we have to do a little bit of porting to make VUnit recognize our test benches, but it's quite straightforward, especially since we had many existing assertions in the test benches. However, they were very varying quality, like one used the bat script, one used the do script, one used the shell script, and so on. So we ported all test benches to VUnit, and they were automatically picked up. And we introduced the main process, and we can split the test cases and so on. One optional step which we decided to do incrementally was to replace all asserts with the checks. Basically not because it was better in every conceivable way, but rather than having one way to do it. We have many available check options from the check library, so it's much easier, convenient to read, since many developers then have written their own flavor of assertions and so on. So we decided on one way to do it. So we have one way to check stuff, and we get the same printouts and the same error messages whether you run whichever test bench you run. So the benefits we got when we were done: we could easily run and add test benches. We could easily read and understand all the test benches, since we had got all the tests structured in the same way. We got more self-checking test benches, since it was easier to parse the output and separate the tests into different test sequences. So we got a more fine-grained control of what parts of the test were failed, instead of having one big monolithic test run, and then you couldn't intelligently parse which test case was failing. So now that got easier. We also added more test bench configuration via the generics, so we got better coverage. We got a single entry point together with TSFPGA, and we also got the possibility of easily writing verification components using VUnit's COM library. Glad we still have faith to think, right? So what's a verification component? Verification component is a simulation level component which realizes an external interface or component. And it hides any signal wiggling and exposes a functional API. This seems to be out of battery. So I have an example here. On the left-hand side, you have the access stream master, which is a verification component. It has the push access stream procedure, which inputs one data into the access stream, and the access stream master does any and all handshaking between the master and the DUT. And on the other hand, on the other side, we have the access stream slave, and we call the pop stream, which opens the access stream channel, and it receives data, and we can use that in our high-level functions and procedures to check the data. So why do we use verification components? Interfaces, they are essential to test. And often people write their code with the best intentions, but we have no clear goal or design philosophy around the verification components. So by having these verification components, we can use a high-level API and close the loop. So we have closed all the interfaces, and we only expose a message API towards the verification components. So by doing this, we can also reuse the code to generate stimuli data, push that to the verification component, and tell the verification component to check the data, and then you push all the data and you let the test bench run. And you don't have to do any manual checking if you don't explicitly want to. You can port the functionality into the verification component instead. And how do we implement a VC? So here in this context, we use the VUnit's communication library, which we can pass messages to and from so-called actors. So an actor is an object in this VUnit in the VUnit library. So we pass messages back and forth from those, without exposing any signals and without running any simulation time. And this is completely asynchronous. So you can push an entire test sequence in 0 simulation time. So basically you do this completely asynchronously and generate new stimuli data whenever you receive a frame, or when you want to push a frame, or you can set up the entire test before. So it makes it time agnostic of when you want to do stuff. So this introduces like a little bit of asynchronicity in our thinking here. I talked a little bit about code reuse. So we could, for example, here we have two different examples. For example, we have the left side here we have an ADC, and one is via SPI, 1/8π²c, and we have used the same packages, same functions to access those. Or we could do the opposite, and we have one interface and several functions. So different VCs can realize different functionality for different functional interfaces. So we extract the interface from the functionality. Next, I will have an example about an SPI slave, which I have implemented. So for example, here we have the purely asynchronous SPI slave interface. We have our test bench, which uses the SPI slave package, and we have two procedures. We have push SPI TH transaction and await SPI RX transaction. And on the top there, you can see that it says generic slave. That's the actor. There's a wrapper record for the actor. So we put these two procedures, push the messages to the actors, or await replies from these actors. So this test sequence It's run in 0 simulation time, and then after it is done, we only wait for the simulation to complete. And suppose we don't want to check any data, we want to realize something else. So we can do an SPI memory VC. So instead of connecting the SPI slave actor, the SPI slave T, to the test batch, we connect it to another entity, which could also be another procedure, if you so like. And here I have used the VUnit's memory type. So by doing this, we can realize an SPI memory, which is quite common. We use like an SPI memory for the boot parameters or product, let's say, or want to store some intermediate data. So we use the VUnit's memory type. Then you get the full functionality of the VUnit API for the memory type. So you can allocate, you can write protect, you can read protect, etc., and initiate this. So the communication here is done asynchronously from the SPI slave, which itself realizes the interface, and another entity which realizes the functionality of the VC. Here we have not even changed the SPI slave. It's the same SPI slave from the previous line, where we could check, and we can just test the SPI interface itself. And now we have another asynchronous communication channel to the SPI slave here instead of to the TD. But the SPI slave verification component remains unchanged. So that's about it. Summary. We have reorganized and forced our code to coexist. We have used VUnit and TS-FPGA together to provide with better standardized ways of testing, single simulation scripts, organization of test sequences, test configuration, etc. And our verification components have provided us with a very high level of abstraction and a modular and extensible way of testing our interfaces. So here I have some tips for VCs, which I have encountered myself. So as the basic gist of it is to start small and build up. So first you realize the interface, and then you add on functionality on top. Or do you really need a memory, or do you just need something which acts as a memory for your intended purpose? Do you only need to, for example, provide the correct boot parameters? Do you actually need a memory, or can you realize it using something simpler? And the base level VC should really only be concerned with passing raw data over the interface. So for example, this SPI slave, which I have shown, is only concerned with sending and receiving SPI transaction and nothing else. It tells the received data and if the channel was closed or not. Separate the interface and the functionality. That makes our lives a whole lot easier. I think asynchronously we can pass data in 0 simulation time to our VCs. And we can basically write an entire test and push it to the memory or the queues or the message interface in the VCs without anything happening unless we tell it to. So that makes it also a lot easier to have many parallel interfaces active at the same time without concerning of race conditions and handshaking. And we could also, of course, offload our stimuli generation to Python. And that's about it.
Any questions? I have one, I guess. So Hitachi Energy is kind of a big company many developers and different sites as well. I've seen that there's been at least job ads for VUnit competence from other sites in Europe as well. So I was thinking, when you come as an external consultant and start saying, okay, you should start using TS-FPGA, you should use VNS, it's a change, so how was that received? I can imagine there was some eye rolling along the way. How did you deal with that?
I have a few of my bosses in the audience. No, generally I started with a personal Git repository, and I started building my way up and introduced the tools to other people, and they could try them for themselves, and was very generally very well received of tools and frameworks.
What are the amount of verification components or VCs you have connected to, and did you see any performance hit when you use, if you scale it up?
We actually saw a reduction in runtime for many test cases, which used this single interface wiggling at a time, and could instead activate many interfaces in parallel. So I know of one example where we reduced the runtime like 10 to 100 times even. So by having this asynchronous thinking and many interfaces active in parallel, and independently verifying and checking the data of each other.
It can be good to know that some people are concerned that if you implement message passing in VHDL, you have to provide some fairly complex abstraction on top of VHDL, and doesn't that consume a lot of performance? And basically, one thing is that we typically communicate asynchronously, so not on every clock edge. So it's less communication. Also, if we think too much hardware and we design verification components, we use a lot of signals, and it's the signals within the design that consumes simulation time. It's not variables. So that's another reason why it can actually see fairly good reductions in simulation times. Anything else? Yes.
How much does VUnit actually help with creation of verification components? Is it just some guidelines on how to build them and how to connect them? Or is that boilerplate code?
Yes, there are examples within VUnit, and as well as for the most common one. Say, for example, Avalon, AXI streams, memories, UART, so on, so you can check that code and see how it's implemented. I also have some next example code on my GitHub for the actual SPI slate code, which is a very rudimentary test bench of just checking the SPI interface itself.
There are also some tutorials and blogs on some. Yes, anything else? Perfect on time, yes. So our next presenter will be Sebastian. He's verification lead on Ericsson. UVM guy at heart, I